So the green wire is being influenced by the yellow magnetic field into the board. What is the direction of the force on the green wire then from the yellow magnetic field? Using that formula down there. See a number of people moving their right hands, which is good. Not just to write stuff down, but writing right hand for the right hand rule. So direction of L, I'm talking about the green wire, direction of L is which way? Okay. Be that way, direction of the current flow. B is which way? Which way is B? B is the yellow. In. So the direction of the force.
Up.
So this is going to be forced upwards. Which direction will the yellow wire be forced? Because of the green magnetic field.
It's doing out.
Magnetic field is out.
So, and L is in the same direction. So it would just be, let's see, it was that way. So it would be.
Right, current's flowing that way. We're doing L cross B. The current is flowing that way.
Yeah.
Magnetic field is out.
Okay.
Down.
Down.
Do that.
As a matter of fact, without doing the right hand rule, we could have figured that out. Why? We need to use the right hand rule for one of them until you get more familiar with it. So let's say we got the green one. How do we know that the yellow force has to be down? Hint, Physics 151. Chapter 4. It has something to do with Newton.
But all forces have an equal but opposite force.
The yellow wire pulls up on the green wire, so the green wire must pull down on the yellow wire. Newton's third law. Now the magnitude of it, of course, I mean, yeah, the concept is great, but where's the math? Well, the concept is I know that the force, the magnitude of the force in this case is going to be ILB. Where L is, since it's two wires, this length would be basically the parallel length. I know that the magnetic field, oh, I really haven't done that part yet.
I have a question.
So we need to do that and then come back to it.
Why are we doing it ILB and not IL cross B?
Oh, here?
Yeah.
Because the way I've set it up is that the magnetic field is perpendicular to the wire.
Right.
So I thought through the direction, so now I'm sort of ignoring it.
Okay.
In 252, I'm more apt to make them less perpendicular.
Okay.
All right, so what is the magnetic field that's actually created? We've talked about, all sorts of stuff, just not doing it in the right order. I'm going to clue you into another trick for figuring out the direction of force. It involves the right hand. If you prefer to look at it from a cross product point of view, go for it. The right-hand rule works because the cross product is the rule. In this particular case here, I've got three regions. I got above the yellow wire, between the wires, and below the green wire. In which section do the magnetic fields go opposite each other? Yeah. So I would expect that we have a weaker magnetic field here than we do here or here, because here they bolster each other, here they're opposing each other. The direction of the force is going to be in the direction of the weaker magnetic field. So if I'm looking at the charge going into the magnetic field, so again, we'll put this magnetic field coming out. I have my proton going in. Well, my proton's going in that way. I know that proton is creating a magnetic field that is coming out on top and going in on the bottom. Here they're opposing each other because I got the external magnetic field and the magnetic field created by the proton in opposite directions. It's weaker on the bottom, the proton's going to be forced downwards.
Because at that point, they are opposite of each other. The
Yes.
magnetic field and the magnetic field.
Yes, yes. As a matter of fact, what I remembered when I started getting back into teaching this stuff long ago, way I did it was that was the way I did it. I looked for where the magnetic field was weaker. I knew that was the direction of the force. And then slowly brought the math more back into it. There was one particular 252 test back when, at 4.5 hours, I said, all right, I'm done. And I have to go. It was 10:30 at night. I have to go home. There was a whole bunch of these right-hand rule problems. And so that I wish I'd filmed it, sent it to music. But the first part of it was, the students, we look at the problem and then it's like hand ballet as they were. I mean, to the right music, it would have been beautiful. Any questions on this before I erase it? So let's talk about Biot-Savart. Spelled Biot-Savart. I found at least one textbook that had said it's pronounced, like it rhymes with Leo Bizarre. So it's Biot-Savart. Even though if you anglicize it, if it went through Ellis Island, you pronounce the T's. The Biot-Savart law is what I will label as actually the second physics equation. And it is the magnetic field created by a moving charge. There are 4 forms of it. These will be calculus-based forms, and so I'm going to put up the calculus-based form of it and then reduce it. Who in here has had some calculus? Okay. It is not a calculus-based course, but I at least want to present it that way, or present the form. And it's one of those things that I fit in a short-term memory, so I should be pretty good by the end of the week on this.
You said Biot-Savart was formulas for magnetic field created by moving magnet?
Yeah. All right, so one form of it, the one I have written here, is in terms of current flow. guess technically, D under the calculus form. When you see the D, for those who have not had calculus, you see the D in front, that just means an infinitesimally small change. So the non-calculus form, you would use delta. So pretty much any place where we've used a delta before, there's a form where if you just use the D in front, it's known as a derivative. So this would be mu naught over 4 pi I delta S across R over R cubed. All right, so form number one. I know that any vector is just a magnitude in a direction. So R vector could be expressed as R, the magnitude, times the direction. Or A vector would be the magnitude times the direction. So if I do that, if I make this substitution here, I'd have an R hat, and one of those R's would cancel out with one of those, and so I'm left with mu naught over 4 pi I delta S cross R hat over R squared. Same formula, just a slightly different form. In 252, I personally find this more useful than this. So if I had a wire, a current running through a wire, and I wanted to figure out the magnetic field at this point right here, I pick some infinitesimally small piece. That would be R right there. It's a vector from some infinitesimally small piece of wire to where the point in question is. Now I know that current is charge divided by time. So I'm just going to rewrite this as mu naught over 4 pi Q over delta T times delta S cross R over R cubed. So all I've done is just put that in the place of the current. Shifting stuff around, I move the delta T under the delta S. This S here, this stands for position, so this delta S is change in position or displacement. If I do change in position over time, what do I get? Change in position over time.
Velocity.
So this now becomes mu naught over 4 pi Q, capital, probably capital Q, or little q, whichever one. Velocity cross R over R cubed, or mu naught over 4 pi Q V cross R hat over R squared. All right, so those are the 4 forms of it. The calculus version, instead of the delta, you put in D. This technically would be delta Q, should be a delta in front of that. And yes, I do recognize that I switched from a lowercase q to an uppercase q. It's fun if we have a single charge or multiple charges. Now, how do you actually solve it? Because if this were a calculus problem, then I would want to figure out the magnetic field at this point. I take some infinitesimally small piece of the current, I look at the magnetic field from that, and then I add all of these up from negative infinity to infinity. I get an answer. It's relatively straightforward calculus physics problem. However, this is not calculus physics, so how do you do it? This was one of the disadvantages of 152, in the fact that I can't derive it without the calculus. There's no quick and dirty shorthand for it. So what I'm going to do is I'm going to present the answer to you. It sort of bugs me, the fact that I can't show you how we get there.
Is it just that there's no way to get there, or just that it's like two different languages?
It really requires being able to do an hand roll.
Okay, yeah.
And so, from a, I feel like I'm missing something there. So if I have a current, go back to that. The magnetic field created by a current is mu naught I over 2 pi r. Now, people see the pi in the bottom and they're thinking circles, especially 2 pi r. What is 2 pi r in the math? It's a formula for something. There are only 2 circle formulas, so that we deal with on a regular basis. 2 pi r is which one?
Circumference.
Yes. How do you know circumference and not area?
Squared.
Correct. This is the magnetic field. A distance r from a straight wire. Infinitely long. Infinitely long straight wire. So I have infinitely long straight wire, I have a current flowing through it to the right, I know my magnetic field is going out on top and on the bottom. If I am here, a distance r away, then that's the formula. The 2 pi r comes from the fact that at this distance from the wire, my magnetic field is traveling around like that in a circle. It is the circumference of that circle at that distance. That's where the 2 pi r comes from. It is often confused with a slightly similar problem. We'll first take the conceptual case. Let's say I have a circle of wire and I have a current flowing counterclockwise. What is the direction of the magnetic field in the middle of this wire? It's a right-hand rule thing. All right, I've seen 2 hand gestures and they are in opposite directions. Out of the board? Luis, you're going with out of the board?
Yes, sir.
And you want to counter that, stand up and just go,
I counter it.
oh, you're gonna
I'm
change
gonna
your mind?
counter myself. It changes, because if it's going in a counterclockwise direction, then when you're looking at current up here, technically it's facing this way now.
The current's facing that way.
Yeah.
All right, so
It's like constantly changing.
when the current is here, what is the direction of the magnetic field?
In that case, it would be into,
Above or below?
above, oh,
It's into the board above. So right hand rule, thumb points in the direction of the current flow, in on top,
okay, so yeah, it is.
out on
Yeah,
below it. When it's here, what's the direction of the current flow, over here? Sorry, what's the direction of the magnetic field over here?
Okay,
And not here?
I'm setting it
Me too.
up and
Matter of fact, no matter where it is, now, technically, the magnetic field created by the current here does extend over to here, but it's much weaker at this point. But the net result is that my magnetic field is coming out of the board. It also works that if you put your hand in the direction of the current flow, the thumb points in the direction of the magnetic field. Now the magnetic field at the center here. So magnetic field at center. Just do magnitude at center of a loop of wire is mu naught I. It's very similar to over there, over 2R. The formulas look very much alike. The mistake that I see students making on this is they see the loop of wire, they immediately think circle, 2 pi r, it's got to be this formula, when 2 pi r refers to the magnetic field geometry, not to the wire's geometry. So loop of wire, I have 2r on the bottom, straight wire, 2 pi r on the bottom. And if you're interested, you can email me, and I don't think I necessarily have the link posted in chapter 22, but if you're interested, send me an email and send you the links if they're not there, and you can see how it's derived with starting using the calculus. Questions before I flip back to the previous problem?